Hi all, today's topic is logarithmic, exponential or anti-logarithmic amplifiers and active filters using Opamp. Let us discuss logarithmic and exponential amplifiers first. To implement a logarithmic or exponential amplifiers, we should have a device whose terminal current is proportional to its terminal voltages by an exponential relation. Here, in the case of a diode, the forward current I is proportional to exponential of V if the diode is forward biased. Similarly, in the case of NPN or PNP transistors, the collector current IC or emitter current IE is proportional to exponentially on the voltage between base and emitter. VBE. So if you are placing these devices at the output or input side of an Opamp circuit, you will get either a log or exponential amplifier. Let us place our diode at the output side of an inverting amplifier as shown. Resistance R. Assume this is my Vin and I am placing a diode like this at the feedback loop. This is grounded. This is V out, positive, negative with respect to ground. Right, for negative Vin, if Vin is negative, your op-amp output goes to positive because it's a negative inverting amplifier. So if your Vin is negative, the diode becomes reverse biased. When diode is reverse biased, there is no feedback in the circuit. So output is saturated. In this case, output goes to positive VCC. Right? If Vin is greater than 0, output is negative, diode turns on. So the circuit has an output V out equal to plus VCC for a negative value of Vin. Right? Let us see what will happen if Vin is greater than 0 or Vin is positive. For Vin greater than 0 or positive values of Vin, there exists a diode current because diode is forward biased, and that diode current is proportional to voltage across the diode. In this particular example, that voltage V is nothing but minus V out because this is at virtual ground due to negative feedback. V plus equal to V minus. Writing the KVL around the loop, negative positive, positive V out, negative positive plus V equal to 0 implies V is nothing but minus V out. I am starting from ground and I am ending at the ground. Closed loop, I should equal to 0. So here voltage equals to diode in the given polarity is nothing but minus of V in this polarity. So the diode current is nothing but the current flowing through R because this is at virtual ground. V in minus 0 by R is current I, and there is no input current to the op-amp. The same current I circulates through diode. So the diode current is nothing but V in minus 0 by R, V in upon R. That's equal to the forward current expression of a diode is expressed as I naught, that is the reverse saturation current, multiplied by exponential V by Vt. V is the forward voltage. Vt is the volt equivalent of temperature minus 1. Here Vt is called volt equivalent of temperature. Its value at room temperature is 26 millivolts. I naught is a reverse saturation current. Since V is positive, V by Vt, Vt is in 26 millivolts and V is greater than Vt always, then exponential V by Vt will be large compared to 1. So you can neglect this one while analyzing the circuit. So V in by R is nothing but I naught exponential V upon Vt, right? And that V value is nothing but minus V out, as we discussed. Minus V out upon Vt. Vt is a constant that's equal to 26 millivolt at room temperature. That implies V out is equal to Vt times ln of natural log of, if you're taking natural log on both sides, natural log of R times I naught upon V in. V in. Or you can put a negative sign here and you can make it as V in upon R I naught. Both are same. So while plotting the curve between V out and V in, if V in is less than R I naught, we will mark R I naught here, R times I naught. If V in is less than R I naught, the argument of a natural log function will be greater than 1. So that will be positive. This is exactly 0 at V in equal to R I naught. If V in is greater than 1, argument is less than 1. So it goes to negative. So that is a transfer characteristics of the given circuit, and V out is not defined at V in equal to 0. So there exists a discontinuity at x equal to 0 axis or y axis, and it varies logarithmically with respect to V in. The same circuit can be implemented by reversing the polarity of the diode, right? Reversing the polarity of the diode like this. Same Opamp, negative, positive, grounded, R, and the diode is connected like this. Now V out is this, V out with respect to ground, and V is nothing but V out itself. So to have a current through the diode in this direction, I, both are same. If the diode is on, there exists a current. To ensure the current in this direction, I am marking it as minus V in. Minus V in. As discussed earlier, if V in is positive, V in is positive, minus V in will be negative. That negative will give you a positive value. As discussed earlier, if V in value is negative, minus V in will be positive. So inverting input positive, non-inverting is grounded. So output goes to minus VCC and the diode turns off. So when V in is negative, you will have a minus VCC compared to the case. And if V in is positive, we'll have a negative input, inverting amplifier output will be positive, so diode turns on the resistor current. And compared to the earlier expression, new V out expression in this case will become Vt ln V in appears in the numerator multiplied by R times I naught due to a change in negative sign here. It will become positive, so this will come up. And as your Vin is positive, and if that value is equal to R times I naught, the argument will become exactly equal to 1, so V out is equal to 0. If V in is less than this, argument will be less than 1, so that will be a negative value. The moment V in crosses Ri naught, argument of log will be greater than 1, so this will be a positive value. So this is a characteristics, and of course there should be a non-linearity here, discontinuity here, because log 0 is not defined. Right? The same circuit can be implemented by inserting a transistor here, NPN transistor with base grounded in this direction like this, and this is my VBE, and VBE is nothing but minus V out in this case. So you'll end up with the same expression here. Similarly, here you can place an NPN transistor, a PNP transistor like this with the emitter grounded like this with base grounded, and emitter connected to output of your circuit, collector connected to the inverting input terminal, and this is my VBE in this polarity, and VBE is nothing but equal to V out. This example, VBE is same as V out. So we'll have same expression here, right, and characteristics also will match each other. Here when V out is positive, this transistor base emitter junction will turn off, so it acts as an open circuit, output will be plus VCC. In this example, if Vin is negative, output will be negative VCC, and this PNP transistor will get open circuited, output is saturated at a minus VCC. Right? If you are placing your diode at the input side, in an inverting amplifier, like this, the circuit will function as an exponential or anti-log amplifier without grounded V in. This is nothing but V, voltage across the diode. In this case, if V in is positive, V in is positive, the diode turns off, and there is no feedback, there exists a feedback loop. This is off, there exists a feedback loop, and of course there won't be any current flowing through R because there is no path to the input side, and of course current into the Opamp is 0 amperes. Then due to the negative feedback, V plus is nothing but V minus, virtually they are at same potential, so V out will be 0. So if V in is positive, V out will be 0. In the other case, if V in is negative, the diode turns on. V in is less than 0, diode turns on. So there is a current in the circuit, I. The same current flows through R. So you can write V out as directly, if the current I flows through R, this product is nothing but I times R. V out is nothing but I times R, and that I flows through the diode, and if V in is negative, diode is forward biased, so there exists a current, forward current, and V in is nothing but V in is appearing between this polarity, ground. So this is also at virtual ground. So positive negative minus V, positive negative minus V in equal to 0, starting from ground, ending at ground, closed loop equating to 0. That implies V is nothing but minus V in. That implies V is nothing but minus. So the V out is nothing but I is exponentially proportional to V, I naught exponential V multiplied by R. So V by Vt will be there as we discussed, right? Reverse vertical of temperature, so reverse saturation current we are neglecting, so there is no -1 term here. So V out is equal to I naught exponential V is nothing but minus V in upon Vt multiplied by R. So I'm taking I naught R to get I naught R multiplied by exponential minus V in by Vt. So V out is proportional to, or V out is equal to, I naught R is in volts, I'm taking it as constant, exponential minus V in upon Vt, or V out is proportional to exponential of V in. So it's an exponential amplifier, and that happens if V in is less than 0. V in less than 0. Right. If you are changing the direction of the diode, the only change is now V will become V in, and if V in is negative, your diode will be off, V out equal to 0. right? So V out is nothing but similar to this I naught times same resistance multiplied by exponential. Instead of minus V in, it will become V in upon Vt. So it is 0. When V equal to 0, it is 1. Exponential 0 is 1. Then it will increase from 1. Of course, there exists a discontinuity here. Sudden jump to 1 from 0 at Vn is equal to 0. Next, we will discuss a low pass filter. An ideal low pass filter is an ideal integrator in which the frequency dependent component, the capacitor, is placed in the feedback loop. C. The resistance is connected at the input side and non-inverting terminal is grounded. This is called an integrator circuit or low pass filter. It is called a low pass filter. Why? Because as omega tends to infinity, your V out by V in or the transfer function goes to 0 as omega tends to infinity. Because as omega tends to infinity, the capacitive reactance is 1 by j omega c. So as omega tends to infinity, this reactance will goes to 0 or the capacitor acts as a short circuit. The moment capacitor is short circuited, there exists a negative feedback, 100% negative feedback, and V plus should be equal to V minus. V plus is grounded, V minus also grounded, shorted, output will also equal to 0. So very high frequencies, output is very low. Ideally, at omega is equal to infinity, output is 0. And as omega tends to 0, very low frequencies, ideally at 0, capacitor is open circuited and your V out upon V in is extremely large, or output of the Opamp is saturated. So at omega equal to 0, V out by V in is extremely large. Then it goes to 0 and it have a value 0 at omega is infinite. So at omega equal to 0, output is at open circuit voltage at omega equal to 0. V out will be equal to a constant, depends on the polarity of V in, either plus VCC or minus VCC, saturated. So ideally, the behavior of a low pass filter should like this, ideally, but it will have a response like this. Ideal low pass filter. Sharp roll off. Right? So this circuit is unstable at omega equal to 0 because capacitor acts as a open circuit and feedback is lost. In practical circuits, low pass filter response will be something like this. There will be an omega equal to omega naught, at which the magnitude of V out by V in reaches 1 by root 2 times of V out by V in its maximum value. Maximum occurs at omega equal to 0. Here at omega 0, we are unable to identify the transfer function because output is saturated. If you are ensuring a stability of the circuit even at omega equal to 0, you will have a plot like this. V out by V in max, then decreases, it will become 1 by root 2 times of maximum value at omega equal to omega naught. We will call it as it's a 3 dB frequency. Right? So let us see how it is function as an integrator circuit, or why it is called an integrator circuit. It's quite simple. The current flowing through the resistance in this direction I will be equal to V in minus 0 by R. I'm assuming feedback exists, and V plus equal to V minus. And the same current flows through the capacitor. Its voltage will be plus minus Vc. So the current flowing through the capacitor I is nothing but I equal to C times derivative of capacitance voltage with respect to time. Here V out and V C is related as Vc equal to minus V out. So the current V in upon R is nothing but minus C times d V out by dt. I'm replacing Vc with a minus V out. So V in by Rc, the negative sign, equal to derivative of V out with respect to time t. To identify V out, I am integrating both sides. So minus integral of V in upon Rc dt will give you V out. So the integration should be from minus infinity to plus infinity. If we are energizing the circuit at t equal to infinity and we are observing, energizing circuit at t equal to 0 and we are observing the circuit at t equal to small t, then I should put a limit from 0 to t. The value is minus V in by Rc dt is equal to V out. Since I have eliminated the time interval from minus infinity to 0, during that interval I was not able to identify the state of the circuit. If initial output is given, then I can add a constant of integration. Let me mark it as K. So that depends on the initial capacitance voltage prior to t equal to 0 interval. Corresponding to that, we'll have an output voltage that is included by the term K. Right? So if you are ensuring that there is no charge prior to t equal to 0 interval all the way from minus infinity, you can neglect it, you can put it at 0. So anyway, V out is equal to 1 by Rc with a negative sign, integral of V in of t dt. V in of t means V in will be proportional to or depends on time interval t, and the limit is from 0 to t. So that is why the circuit is also called as an integrator. The same analysis can be done by replacing the capacitor with a capacitive impedance in S domain. So this is marked as capacitive impedance is 1 over S C. We wrote it as 1 over J omega C. J omega is called S, so 1 over S C. So it's an inverting amplifier, so voltage gain V out by V in can be directly written as negative sign due to the inversion. Feedback path resistance or impedance is 1 over SC upon the input side is R. So it will give you 1 over RCS. The transfer function V out by V in. It is clear that V out by V in tends to infinity as omega tends to 0 because S is j omega, it is in denominator. If I am multiplying numerator and denominator with j, V out by V in will become minus j upon omega RC multiplied by S was j omega, so j multiplied by one more j. So j square will become minus 1, so this will become j upon omega RC. This minus and the minus will cancel each other. So this is the transfer function of your integrator. It is clear that angle is nothing but plus 90. J omega RC implies no real term, so angle will be tan inverse infinity and J is on numerator. So the contribution of the circuit with respect to the angle is angle of V out by V in is nothing but plus 90. Let us observe the behavior of the circuit with respect to omega and magnitude j upon omega RC, that is nothing but root of s square plus b square. A term is 0, root of b square is nothing but b itself, and that b value will be equal to 1 by omega RC. So if you are expressing it in decibels, 20 log 1 by omega RC. And if omega equal to omega 1, I am defining my magnitude as m1. So m1 will be 20 log 1 over omega 1 RC. Right? If I am taking another magnitude m2, that's equal to 20 log 1 over omega 2 RC. And let us assume that omega 2 is 10 times that of omega 1. I am changing to a decade 10 times of the initial frequency. So that will become 20 log 1 over 10 times omega 1 is omega 2 multiplied by R and C. That is what is called M2. If I am taking the difference between M2 and M1, that will become 20 log 1 over 10 omega 1 RC minus 20 log 1 over omega 1 RC. So that will become 20 log omega 1 RC on numerator divided by 10 omega 1 RC. Here the numerator omega 1 RC will get cancelled. So that will be equal to 20 log 1 over 10, that is minus 20 log 10, that's equal to minus 20 dp. So if we are moving from omega equal to omega 1 to omega equal to omega 2, that's equal to 10 times omega 1. If you are moving over a decade of frequency, your magnitude should come to 20 decibels negative. So we'll call it as magnitude here is m2, magnitude here is m1. So m2 minus m1 divided by omega 2 minus omega 1 is the slope. So over a decade, the slope will be equal to minus 20 decibels. Minus 20 dB over a decade. 10 times omega 1 is omega 2. Right? And the value, the point at which magnitude crosses 0 point is nothing but this is my general expression of magnitude. When argument of log equal to 1, 20 log 1 will be 0. So argument of log will be 1 if omega is equal to, since omega is a variable, omega equal to 1 over RC. Omega equal to 1 over RC. Right? So the integrator has an initial slope of minus 20 dB per decade. And it is unstable at omega equal to 0. To ensure the stability of an integrator at omega equal to 0 or a low pass filter at omega equal to 0, I am inserting one resistance in shunt with the capacitor. And I will call that resistance as, let me call it as R2 and C2. This is R1. Input is applied here. This is grounded. That's my V out. Here also the transfer function V out upon V in can be easily identified by taking the parallel combination of these two. So I will call it as ZP divided by, this is R1 itself with a negative sign. So while writing ZP, we have to take two impedances in parallel. And as we discussed earlier, C2 impedance will be 1 by SC2. So ZP is nothing but 1 by SC2 in parallel with R2. That is nothing but R2 divided by 1, R2 multiplied by 1 over SC2. That is nothing but R2 upon SC2 divided by 1 by SC2 plus R2. R1, R2 divided by R1 plus R2. Z1, Z2 divided by Z1 plus Z2. So this will become negative sign. So this will become, this is SFP. So this will become, taking the LCM, R2 on numerator divided by 1 plus R2 C2S. So my V out by V in will become minus of R2 by 1 plus R2 C2S multiplied by R1 in the denominator. So as omega tends to 0, this S term will goes to 0. S is j omega. As omega tends to 0, S term will goes to 0. Then denominator will be R2 divided by, denominator will be 1 plus 0 times R1, that is R1 itself. So as omega tends to 0, this transfer function tends towards minus R2 by R1. So compared to earlier cases, at omega equal to 0, we were unable to mark the y value or the transfer function that was very high. Saturated case here, even though the capacitor is open circuited, the feedback is not open, there exists a resistive path. So minus R2 by R1 is the voltage gain. So this is nothing but minus of R2 by R1. So I am taking the magnitude. This will be R2 by R1. Right? As omega tends to infinity, denominator will become larger. So voltage gain goes to 0. Very low value, and it touches x-axis at omega equal to infinity. Right? So this is a behavior of an low pass filter circuit, or an integrator with a capacitor is placed in shunt with the resistance R2. Right? So the maximum gain is nothing but R2 by R1. In the transfer characteristics, or in the gain versus omega frequency plot, there exists a frequency at which omega naught, at which your gain will become 1 by root 2 times of the maximum gain. Magnitude is R2 by R1. To identify that, we are taking R2 by R1 is a term, then 1 over 1 plus R2 C2, if you are expressing it in omega, 1 plus J omega R2 C2, because S is nothing but J omega. So to make it as 1 over root 2, this entire term should be equal to 1. So that 1 plus J magnitude will be 1 by root of A square plus B square, 1 square plus 1 square, 1 over root 2. So J coefficient should be equal to 1. That happens when omega is equal to 1 by R2 C2. So that is called omega naught, 1 by R2 C2. That is called 3 dB or cutoff frequency. You should remember that a low pass filter should have a high frequency cutoff, a high cutoff frequency, that is called omega h. A low pass filter should have upper cutoff frequency omega h, and that value is nothing but maximum voltage gain reduces to 1 by root 2 times, and this was the maximum voltage gain magnitude R2 by R1. To make it 1 by root 2 times, the complex term magnitude should be 1 over root 2. To make it 1 over root 2, A square plus B square, B value should be equal to 1, omega R2 C2 should be equal to 1, implies omega equal to 1 by R2 C2. That is called 3 dB cutoff frequency or upper cutoff frequency of a low pass filter. A low pass filter will have an upper cutoff frequency because as frequency increases, the magnitude of voltage gain decreases. That's all about a low pass filter or an integrator circuit. The same response can be obtained by placing an inductor at the input side. V out grounded, V in. This is R, this is L. In S domain, inductive impedance is L times S or J omega L. S equal to J omega. R is nothing but R itself. So the transfer function V out by V in is equal to Z2 divided by Z1. Z2 is R itself. Z1 is Ls, negative sign due to inversion. So this will be equal to R upon J omega. S is J omega L. So that is similar to our expression here in the first case. V out by V in is J upon omega R C. or J upon S R C. So omega with a negative sign. So if you are multiplying with J, we get minus J R upon J square, that is minus omega L. So this will become positive R upon omega L with a J term. So angle is again positive 90 degrees. Rj by omega L, Rj by omega L, J by omega Rc. The only difference is R appears in the numerator. So angle will be positive. It behaves as a ring decorator because the transfer function is inversely proportional to omega. At very high frequencies, inductance act as an open circuit. Inductance act as an open circuit, very high frequencies. So V out will be 0 at very high frequencies, omega. Inductance open circuited, V out will be equal to 0. This is at virtual ground due to the feedback. No current into the Opamp, no current to the resistance. So V out will be 0 itself at very high frequencies. As frequency decreases, ideally at omega equal to 0, the inductor acts as a short circuit. So there exists a problem here that the circuit demands V in here at the inverting input, and V plus equal to V minus condition due to the feedback demands a virtual short here. So the circuit will not function properly as the omega tends towards 0. So in this case, if you are trying to identify the voltage gain of the circuit, V upon V in magnitude, R upon J omega L, omega is equal to 0. It will goes to infinity and the circuit is not functioning properly. So we'll have the same problem as we discussed in the earlier case. So it's not stable at omega equal to 0. Right. So you can place the capacitor at the input side. Capacitor at the input side here. This is grounded. R is connected here. And this is my V. Similarly, you can place the resistor at the input side, grounded, and an inductor at the output side. And this is V in L, R, C, R. So if you are writing the transfer function, V out by V in here will be nothing but negative of R, Z2 is R, divided by Z1 is 1 over SC. So you will get minus RCS or minus J omega RC, because S is nothing but J omega. Similarly here, V out by V in will be Ls, as we discussed. L is replaced with Ls divided by R. That's equal to J omega L upon R. Right, with a negative sign. So both case it appears proportional to omega on the numerator. So it acts as a high pass filter, because if you are taking the magnitude here, this will become omega L by R. Magnitude here divided by V in will become omega RC here. So both circuit act as an high pass filter. When omega equal to 0, magnitude of voltage gain V out by V in is 0. Then it increases. When omega tends to infinity, the voltage gain also goes to infinity. So low frequency range you have a low gain, and high frequency range you have high gain. It's a high pass filter. And of course it won't be stable at omega equal infinity, because at omega equal infinity gain will be minus infinity, or magnitude of gain will be infinity. So it's not stable at omega equal to infinity. And since it is a differentiator circuit, why it is called a differentiator circuit? Let us see that the current flowing through the capacitor is nothing but IC is equal to C dVc by dt, and voltage across the capacitor is nothing but V in itself, because this is at virtually ground. So capacitance current flowing through the capacitor is IC, nothing but C times dV in by dt, and the same current flows through R. So V out will be minus IC times R. Same IC flows through R also. This is at ground. Polarity is plus minus. This drop is plus minus. So V out is minus ICRC, minus IC into R. Sorry, IC into R. Then IC is nothing but C times dV in by dt times R. So we'll write V out is nothing but minus RC derivative of V in. As the output is proportional to differential of the input, it is called a differentiator. Similarly, this also will be a differentiator. Right? Differentiator circuit or high pass filter. The ideal response of an high pass filter will look like this. Sharp change here. Gain will be 0, V out by V in, magnitude will be 0, then magnitude goes to maximum value. Ideal high pass filter. Remember, for your high pass filter, you will have lower cutoff frequency or omega L. In these two circuits, lower cutoff frequency is not defined. We have to rectify the instability at omega equal to infinity by adding a shunt resistance across L or C. This will become open at omega tends to infinity, so you can place a resistance here. This will become short while omega reaches infinity, so you can insert a series resistance. So it will rectify the issue at omega tends to infinity case. Then you can define upper and lower cutoff frequencies. So that's all about high pass filter or differentiator circuit. Right. Let us have another kind of filter circuit. Right, I'm using my low pass filter here, high pass filter here, and I am giving to a summer. It's a adder circuit, not multiplier. Summer plus adder, and my input is common. call it as V in, and this is my out. If these two are ideal low pass and ideal high pass filters, they will have a response like this: ideal low pass, ideal high pass. High pass filter have a lower cutoff frequency FL, low pass will have an upper cutoff frequency FH. Then what will be the response at V out? V out will look like an all pass nature if FH of your low pass equal to FL of your high pass. If both are equal, 0 plus a value will give you that value. At FL, this will become 0 and this is at 1. So greater than FL, this will become 1, this is 0. So if both are equal exactly, we'll have an all pass match. If FL is greater than FH, so if you're moving this away from FH, at the output you will have a dip. And that dip, if FL is FH, will be proportional to the interval FL minus FH. So this is all pass filter. This is band reject filter. Right? If you are adding these two. So a filter, different kind of filters can be implemented by adding or subtracting the response of low pass as well as high pass filters. Remember, low pass will have upper cutoff frequency, high pass will have a lower cutoff frequency. And these two are ideal responses. Practically, FH and FL is defined as maximum gain reaches to 1 by root 2 times of that value. FL is also same, maximum gain reduces to decays to 1 by root 2 times of the maximum voltage gain. Right? Okay. Let us discuss another circuit in which let us have a few more circuit and let us identify the type of filter. Here I am using one LC series circuit here shunt with a resistor R2 L and C. This is R1, this is Bn. And positive input is grounded. Here, magnitude of or the voltage gain is nothing but minus ZF divided by Zn. ZF is a parallel combination of LC series circuit and R2. So we'll have SL plus 1 by SC in parallel with 2 divided by R1, the negative sign. Identifying this transfer function and rewriting it to identify the behavior with respect to omega, it will take time. Instead, our aim is to identify the type of filter. As you know, the series LC circuit will have an impedance SL plus 1 by SC. So that is nothing but j omega L plus 1 over j omega C. So that is nothing but j omega L minus j by omega C. The exists a frequency at which the sum of these impedances will goes to 0. That omega is called 1 by root LC, omega naught resonant frequency, or omega R resonant frequency. At a resonant frequency, both impedances will be equal in magnitude and they will cancel each other. Omega L equal to omega RC, 1 upon omega RC. Then this will become short circuit. The moment it is shorted, the resonative feedback V plus equal to V minus, this is grounded, V out will goes to ground. So in your characteristics, V out versus V in, V out upon V in versus omega, in your frequency characteristics, at omega equal to 1 by root LC, you will have a dip in the voltage gain. Either side of these frequencies, if omega tends to 0, capacitor open circuited, inductance act as a short. So gain will be nothing but R2 by R1. If you are taking the magnitude, R2 divided by R1, it's an inverting amplifier. Gain is minus R2 by R1. The other branch is open, so it will decrease, reaches to 0 here. From omega equal to omega naught or 1 by root LC, if frequency goes to infinity, your capacitor acts as a short circuit, inductance acts as an open circuit, then this branch is open. Magnitude of gain will be again R2 by R1. Right? So these kind of circuits will have a band reject filter response because gain is too low in a particular band of frequencies. Okay, so it's a band reject filter. If you are placing your inductor and capacitor in parallel, C and L, at omega equal to omega naught or omega equal to resonant frequency 1 by root LC, the impedance of the parallel circuit will be maximum. Then you will have a peak at omega equal to omega naught and decays at the other side of your resonant frequency. As omega tends to infinity, capacitor acts as a short circuit, so output decays to 0. At omega equal to 0, inductance acts as a short circuit, output decays to 0. So in a particular band, you are having higher gain than all other frequencies. So this is called band pass filter kind of response. So that's a band pass filter, right? Let us take another circuit in which an Opamp and resistors are involved. Equal resistors are here, C here, are here, and this is my V in, both input common, negative and positive. If you are asked to identify the type of filter, then again let us assume two extreme conditions, omega equal to 0. Omega equal to 0, a capacitor acts as open circuit. When capacitor is open, no current flows through R. This is at 0 volt, grounded. So this is an inverting amplifier circuit. So V out upon V in will be equal to minus R by R, that is minus 1, right? At omega equal to 0. If omega is equal to infinity, capacitor acts as a short circuit. So V in comes here at omega is equal to infinity. V in comes here, negative feedback, V plus equal to V minus. V minus is nothing but how much? V out and V in equal resistors. So V out plus V in upon 2. That should be equal to V in, V plus equal to V minus. Right? So V out is nothing but twice of V in minus V in. So V out is nothing but V in itself. So V out by V in is nothing but plus 1. Right? So our two extreme cases, output is equal to plus V in or minus V in. If you are writing the transfer characteristics of the given circuit, V upon by V in, if you are writing the voltage gain of the given circuit, you will get it as 1 minus RCS upon 1 plus RCS. Its magnitude will be on numerator S square plus B square 1 plus omega square R square C square upon root of 1 plus omega square R square C square. So magnitude is always equal to 1. So this circuit acts as an all pass filter, and its phase, output phase with respect to input phase, varies between minus 1 implies 180 out of phase, plus 1 is 0 phase shift. So phase varies from 0 to minus 180. And magnitude always remains at 1. So it's a all pass filter circuit.